И я рад представить последнего докладчика нашей конференции. Кирилл Глебович Камалутдинов расскажет про приложение теоремы об общем положении для множеств дробной размерности. Пожалуйста, Кирилл Глебович, вам слово.
Okay, so my slides are in Russian, so I will try to talk in English. I will talk about an applications of general position theorem for fractal sets. Fractal sets means here a sets of with a fractal Hausdorff dimension. So I usually consider not non-arbitrary fractal sets. I consider a self-similar sets. So a self-similar set is defined by the system of contraction mappings. If we have a system of contraction mappings, then a non-empty compact set such that it can be represented as the union of its own images by this family of mappings is called a self-similar set generated by this family, or an attractor of this family, or also invariant set of this family. So it is for any family of contraction mappings, and especially for contraction similarities, it exists and unique. The first possible example of such set is a counter set, classical counter set, which can be constructed by if we divide an interval on three equal parts and draw out the middle part, and repeat this process on the remaining parts infinitely many times. So, and the second example is the Sierpinski triangle, where we have three parts that are similar to the whole. So it is generated by three contraction mappings with a contraction ratio 1/2. And for a counter set, there will be two contraction mappings with a ratio 1/3. So if we will consider families of fractal sets, parameterized families, for example, a parameterized family of sets A, T, and BT in Rn, then we will call such parameters for which we have a non-empty intersection are exceptional parameters. So exceptional parameter is a parameter when we have an intersection between sets. And so we also will consider separation conditions for fractal sets. The strong separation condition means that there are no non-empty intersection between copies of self-similar set. An open set condition means that there are an open set such that it maps inside it, and its images do not intersect each other. And the weak separation property means that an identity mapping is an isolated point in such a family of sets or of mappings where I and J are incomparable multi-indices. So multi-index mean the set of indices. So it means that I apply SI1, SI2, SI3, and so on. So we have, our work is motivated by the question about connection between the intersections of copies and the separation properties. So, for example, we have a question for those exceptional parameters. how large the sets of parameters for which we have a non-empty intersection, an empty intersection between particular copies, for which we have a non-empty intersection with a finite intersection, and for which we have a intersection of the form that it is also an image of the whole set. So the first case, if we imply the first case for every pair of copies, then it will be the same thing as a strong separation condition. But we do not know how an open set condition relates to the finite intersection property. And we do not know how weak separation relate to this third property that we call strict overlap. So what do we know about separation conditions and why they are such important? The strong separation condition provides an open set condition, and it provides a weak separation property. An open set condition provides that we can calculate our Hausdorff dimension of the whole set as a solution of such an equation. It is a Morans equation. And we also call this solution as a similarity dimension of the system. And an open set condition is important because we also can say that our Hausdorff measure of our set is strictly positive, only in this case. So the question arises, suppose we have a finite intersection between copies. Is it possible to have a finite intersection, but zero measure? Of course, it means that there are no open set conditions, that only maybe weak separation property. So we prove the theorem of general position for fractal sets that allows us to solve many questions about such relations between separation conditions and intersections. And the theorem says that if we parameterize our sets by the functions phi1 and phi2, our parameterized family of fractals, where t is the parameter of the whole family, and f1 of tx parameterizes the first set, and f2 parameterizes the second. So under those conditions on phi1 and phi2, which means they are Hölder with respect to x, and anti-Hölder with respect to their difference is anti-Hölder with respect to the parameter t. We have an estimation of Hausdorff dimension of a set of exceptional parameters. The set of parameters by which we have a non-empty intersection between the corresponding sets images phi1 and phi2. So the Hausdorff dimension of such a set of exceptionals may be estimated by this Hölder parameters from those inequalities, and the Hausdorff dimension that depends on sets L1, L2, where we take x1 and x2 variables, and also by the dimension of set D, where we take a parameter t. So what does it mean for us? if we have such an estimation here, this will mean that because the dimension of the set of exceptionals is strictly less than the dimension of the whole set of parameters, where we take parameter t, then it will mean that the set of exceptionals is nowhere empty, nowhere dense in the set of parameters, in the space of parameters. So this means that our parameterized sets do not intersect each other for almost all parameter values. The simplest application of such a theorem is the following. If we have just an arbitrary sets A and B in Rn, and we, for example, translate one of them, just translate one of them by the vector t, and then consider the intersection between translated set and the second one, then the Hausdorff dimension of the set of such parameters under which we have a non-empty intersection will be estimated by this Hausdorff dimension of the A cross B. So this means if the dimension of A cross B is less than S, then N is strictly less than N, then we can say that A and translated B will have an empty intersection for almost all translations. The same thing is true if we, for example, extend our second set B. We multiply all the points of B by parameter t, and if B do not have 0 in its closure, then we have the same estimation where one is n equals to 1 because the parameter t is just some real number. So the more interesting application arises when we consider self-similar sets. Suppose we have a family of similarities, contraction mappings in Rn, and we, for example, change the last one of them. Suppose it depends on the parameter t, where t is just a translation applied to some mapping which does not depend on t. So then, if we have such an estimation for similarity coefficients of the first one, the last one, and the maximum in the sum less than 1, then the dimension of the set of exceptional parameters for the intersections between the first copy and the last copy will be estimated by the similarity dimension of this whole family. So if this similarity dimension is less than is small enough, is less than 1 divided by 2, then we can say that our family have no intersections between copies for almost all translations. As a corollary, we can say that if we apply different translation vectors in every mapping, then it is also true that if maximum of our coefficients is less than 1 divided by 3, and the similarity dimension of this whole system is less than n divided by 2, then the system will satisfy the strong separation condition. This means that it has no intersection between between different copies for almost all parameter values, for almost all translation vectors. The same thing is true for if we have some extension instead of translation. Suppose I multiply some fixed map J on a parameter T, on a real parameter, and in this case I just need some additional hypotheses A and B to get the same estimation for a dimension of exceptional sets, but this estimation will depend on our similarity dimension depends on the parameter, so we should take a supremum in this case. The corollary, the same is true that if we take such extensions in every mapping, then under some hypothesis we also have a strong separation for almost all such parameters T1 and Tm, so on. So this only is those two theorems and corollaries are only says something about the strong separation condition. But what if we have a non-empty intersections between copies? What about an open set condition and weak separation property? The first interesting example is the twofold counter sets. If we consider the system of the fourth map for contractions of such form, two constructions with a ratio p and two with a ratio q, with a fixed points 0 and 1 correspondingly. So this set will be constructed for will consist the four its own copies, and the question is about that under which conditions we have an intersection between the first and the second copy, which will coincide with some image of the whole set. So in this case, we'll say that our set is twofold counter set. So we proved using general position theorem that the set of such parameters p and q, which are less than 1 divided by 16, for which k is a twofold counter set, attractor of such system is twofold counter set, have a full measure in the set in the space of parameters. So for almost all p and q that are less than 1 by 16, are an attractor of such system will have the intersections of such form. The interesting thing that this system does not satisfy even weak separation property. Not only open set condition does not hold, then do not hold, then but also weak separation property breaks here. But nevertheless, we have a simple way to calculate the Hausdorff dimension of such set through the such equation. There are also several interesting properties about these sets, but I will continue to another example, which are the most important. The most important application of our general position theorem is about the family of 6 mappings, 6 contraction mappings. You can see them how they map the interval 1, 0 on this picture. So the first, the second, third, fourth, fifth, and sixth parts. So the question is it possible to choose such a parameters P, R, and Q such that this set will have an only one point intersection between the third and the fourth copy here. You see, they are the images of the whole interval overlap each other here, obviously. But is it possible to have such a self-similar set attractor that its images do not overlap each other except only one point H? Yes, it is possible, and moreover, it is possible to break some separation conditions also. So we prove for such system of contraction mappings, we prove several properties which allows us to say that if we have on only one intersection point between the third and fourth copies, then it is equivalent to that we have no intersection between such images of iterations of the first mapping applied to the right part of our set, if we just drop the first part. So it allows us to apply our general position theorem to all such images of the whole set, and check that for almost all parameters we will have an empty intersection. And so we will have one point intersection between third and fourth copy using general position theorem. So in this case, we will say that the system will have a unique one-point intersection. So we prove that for almost all parameters such that R is less than 1 divided by 36, and P is less than R, and Q is less than R, this system will have a unique one-point intersection for almost all such parameters. And also, what is interesting, the Hausdorff dimension can be calculated just as a similarity dimension. So it will be calculated from the simple equation from the parameters P, Q, and R. But we can choose such P and R's such that the system will not satisfy even weak separation property. And I remind that if we have an open set condition, that then our Hausdorff measure is strictly positive under corresponding Hausdorff dimension. But if we do not have an open set condition and even weak separation property, this means that our measure is 0. So the most interesting thing about this example is that only one point intersection between copies can drop our Hausdorff measure to 0. When Hausdorff dimension is calculated by the same from the same equation as for the case where we do not have intersection at all. This question is very important because for many years, many researchers think that it is impossible to do such a thing. But we constructed an example using our general position theorem that it is possible. This means that one point intersection and finite intersection is not enough to provide us an open set condition and even weak separation property. So the results of the last example were published in nonlinearity in last year, and the previous results are published in previous years, and the 15 year we first tried to construct any examples using such general position theorem, but the first example was about curves in three-dimensional space, and it was very untrivial. So untrivial also in a construction. So we do not even we do not even simplify this text yet to anyone to understand it. So it is only on archive now. No questions, please.
So if anybody has any question.
Так, можно задать вопросы, да?
Да, пожалуйста.
Я не понял, вы закончили? Алло.
Да, Александр.
Да, я закончил.
Ну, я скажу тогда пару слов в порядке комментариев. Ну, вот кантовые множества возникли более 100 лет назад и на протяжении вот столетия служили таким неисчерпаемым источником контрпримеров в анализе. Ну, допустим, лестница Кантора, которая дает функцию, производная которой почти всюду равна нулю, а сама функция не константа. И много-много других примеров. Но вот в последнее время возник интерес к фрактальной геометрии. Он был связан с разными причинами. Одни причины – это теория дискретной группы, их предельных множеств, теория пространства Мюллера и так далее, и так далее. И надо было каким-то образом оценивать поведение вот этих вот фрактальных множеств, допустим, с точки зрения размерности. Было обнаружено, что в размерности у них иногда не совпадает с размерностью всего пространства, а меньше. И появились довольно красивые формулы, типа размерность равна логарифму 2 делить на логарифм 3, или что-нибудь в этом духе. Но эти формулы всех, как говорится, немножко вдохновляли. Казалось, что это очень простой предмет для исследований, поскольку формулы получались из того, что фракталы самоподобны. Ну, скажем, увеличиваешь его в 2 раза, он остается примерно неизменным, и за счет этого можно записать довольно простое уравнение, которое вот так или иначе оценивает его размерность. Но при глубоком исследовании оказалось, что эта размерность, в общем-то, такая достаточно виртуальная. Мы можем найти красивое число, которое не обязательно совпадает с реальной хаусдорфовой размерностью этого объекта. А чтобы оно совпадало с хаусдорфовой размерностью, надо использовать условия вот взаимных пересечений. Но тут 3 типа пересечений есть. И тогда действительно красивое число – это реальная характеристика нашего фрактала. Но вот в этой работе показано, или точнее найдена тонкая граница, когда вот классические способы вычисления хаусдорфовой размерности работают, а когда они уже перестают работать. Классических канторовских множеств здесь было недостаточно, чтобы продемонстрировать это тонкое отличие, поэтому были введены двойные канторовые множества, которые позволили построить вот такую вот серию контрпримеров с одной стороны, а с другой стороны посчитать хаусдорфову размерность во многих важных случаях, когда вот эти условия своего пересечения уже заведомо не выполнены. Так что результат, конечно, очень интересный, надеюсь, имеет будущее. Ну и еще надеюсь, что Глеб Кириллович в самое ближайшее время представит и защитит свою кандидатскую диссертацию. Я хочу пожелать ему в этом всяческих успехов.